Hello, my name is William McKillop, and this is Lab 3 Circuits. So the purpose of this lab is to predict the behavior of circuits containing resistors in both parallel and series form. Use voltmeter and ammeter to measure the current and potential difference across the circuit, and examine behavior of capacitors and resistors. And so look into the main lab results, or the node and loop were satisfied, and the RC is time dependent. So we use the loop rule, which is delta V round trip equals 0, the node rule, which is current in equals current out, and Ohm's law, which is V equals current times resistance. So for our procedure, we create both series and parallel circuits, measure potential difference and current using voltmeter and ammeters, and then we graph the results. And the initial conditions were two 1.5 volt batteries, a 47 ohm and a 100 ohm resistor, and two ammeters. So for system and surroundings, the system was the circuit and the surroundings were everything else. So this is our data. For the first one, I equals 0.02A. And if the ammeter was reversed, then the current shows negative current. And then for circuit 2, since the current is not connected, we have a current of 0. But we still have a potential difference because of the batteries in the current, which is 3V. So here we have measurements of voltage at different segments. So at AB, there's 3 volts due to the battery, and then there's 0 volts where there are wires, and the ammeter was 0 as well. And then it becomes non-zero when it passes through resistors. And as you can see, with CD is negative 0.96, EF, these are all non-zero, but we see that delta V round trip is 0. So for calculations, we just use the Ohm's law, and we found these values. The first resistor, which would be 47 ohms, and the second resistor 100, and then the wire and ammeter would be 0 ohms. So the potential difference visually, we have our graph to the right. Wires have negligible potential difference, and battery has a positive potential difference, and resistors have negative potential difference. An important thing to note here is the delta V round trip ends up being 0. So for the node rule visually, we have that the ammeter has negligible resistance, and current from battery is split at the node due to the node rule right here. And most current moves around the resistor, so when it moves through the right part of it, it's 0.17, and then at the bottom toward the left, it's 0.17. So RC circuit, so the light bulb lights up immediately and then dims quickly. The capacitor is charged when bulb is out, and removing the battery causes the light bulb to light up, which means the capacitor is discharging. And we measured how long it would take to do this. So um, 10 ohms is 8.2 seconds, 20 ohms, 19.7 seconds for the capacitor charge, and the discharge 10 ohms would be 9.8 seconds, and then 20 ohms be 20.3 seconds. So we graphed this data as the time went on, and we got, for our experimental value, 5.828 seconds. Our RC estimated was 6 seconds, and our accuracy was 97.12. We also linearized the graph as well to get these values and understand our data. What if you use a real battery to charge a real capacitor with no resistor in the circuit? Well, a capacitor will take more time to charge and would not charge instantly. And what if you use an actual ammeter instead of an ideal simulated ammeter? Current reading would be lower because of the resistance in the amp. Thank you very much.